Hello, this is Dr. Olson from Daytona State College again for Physics 1054. We're in the middle of Chapter 14 talking about heat. In the previous video, we defined what heat is, and we looked at how heat can either affect the temperature or the state of matter. When it affects the temperature, we call this specific heat, and when it affects the state of matter, we call this latent heat. So now here in this video, we are going to quickly touch on something called calorimetry, looking at the math of exchanges of heat. We'll talk about how to solve these types of problems. We'll do an example of calorimetry in a subsequent post, so stay tuned for that. I will let you know when that is up. Then after we talk about calorimetry, we'll talk about three types of heat transfer: conduction, convection, and radiation. First, a comment about calorimetry. There are three types of environments that we can deal with. In a closed system, you basically have a lid on a jar, so whatever's in there stays in there, the mass stays the same. However, you can still lose energy through, say, emitting heat out to the air around you. That would be a closed system where the energy can be exchanged, but the mass is constant. An open system would be like your jar, but now you take off the lid. So yes, you lose energy, but you also have the possibility of losing mass as well. An isolated system now would be a closed system, but now energy cannot be transferred anymore. So ideally, we like to work with isolated systems because then we can keep track of every joule of energy and account for every single thing that happens. In an isolated system, if you have an object that loses energy, then you have another object that has to gain that energy. So the heat lost by one object has to equal the heat gained by another. So as a result, if you take the difference between the heat gained and the heat lost, then that tells us that the total exchange of heat is equal to 0. So how do we solve calorimetry problems? First of all, we need to identify what type of system we're dealing with. Is it a closed system, an open system, or isolated system? Because if it's a closed or an open system, then we have to take into account the environment around it and those exchanges of heat as well, because they will affect our budget of heat. And we also have to find out if all the significant sources of energy transfer are known and are calculable. Second step is we have to apply the conservation of energy. As we know, energy cannot be lost or destroyed. It's only exchanged from one form to another. So we have to account for all of those changes of energy. Now, if there is no change of state of matter or change of phase, then all of your heat transferred is going to be between mass, specific heat, and temperature change. In other words, we're just dealing with specific heat, a change of temperature. However, if there are phase changes, then we will need to have latent heat terms inside of our equation as well. So, easiest way to determine everything, I have found at least, is using the chart of specific and latent heat. Mark where your starting temperature is, mark where your final temperature is, and just trace a path going from one point to the other. You have to include every change of temperature and every change in state of matter along that path in your calorimetry equations. Make sure that each term is in the right place and that the temperature here it says make sure the temperature changes are positive. What's most important here is that you're indicating heat lost versus heat gained so that they all add up to a net change of 0. That's really what we're looking for. Point 6, when everything's all said and done, all objects are going to be at the same final temperature. The system has reached equilibrium, so everything will be at the same final temperature. Finally, once you have that, you can solve for the appropriate variable, enter your numbers, solve the problem, check your units, so on, like we always do. So those are some basic steps to help with solving calorimetry problems. Again, in the next post, I will give you a couple of examples in how to do some calorimetry problems. Let's talk about the 3 basic types of heat transfer: conduction, convection, and radiation. Conduction is simply the exchange of energy or heat through the collision of molecules. You can think of pool balls. As one pool ball hits another, the energy is transferred from the first ball into the second. Same idea with molecules. Energy is transferred from the moving molecule to the second molecule. How much heat flows per unit time? The rate of heat flow is going to depend on the difference in temperature between the two objects, how far the heat has to travel, and the conduit through which it is traveling. We need to know both the size of the conduit as well as the what material it's made of. This K determines, it's called the heat conductivity. It will it describes how well a certain material conducts heat, and that's what we saw in the previous video. I take that back. I guess we didn't see the heat conductivity in the previous video. I'm sorry, I was remembering this here. Thought it was in the other video. That's okay. Anyway, so we have materials with large conductivities. They will conduct heat quite quickly, whereas materials with smaller conductivities conduct heat much more slowly. Great example of this. You're cooking in the kitchen with a stainless steel spoon. Iron and steel have a conductivity of 40 joules per second meter degree Celsius. And so that heat actually travels up fairly quickly up the spoon. So if you cook too long with a metal spoon, pretty soon the spoon gets hot and you can possibly burn your hand. A solution is to use a wooden spoon, which has a conductivity of 0.1. So since it's a smaller conductivity, it will not conduct heat quite as quickly. It'll take much, much, much longer for the wood to heat up to a dangerous temperature. So these objects with smaller heat conductivities are called insulators. Okay, so now we could talk about convection. Convection occurs when heat flows through the movement of molecules. So let's say that you have a mass of water that is, we'll say it's warm. That warm mass of water then moves from one place to another. You've probably experienced this as you've sat in a swimming pool, nice and warm, and then all of a sudden the water gets cold. You just have a sudden chilly water hits you. What's happening is the warm water, which has more energy, flows away. It moves from one place to another. That is the idea of convection. It's the motion of the fluid which takes the energy with it. Now, the general pattern is that when you have a fluid that is warmer than its environment, it's going to rise. When you have a fluid that's colder than its environment, it's going to sink. And so you end up with what's called a convection cycle. Now here's a video that shows a pretty good convection cycle. Now you can see the red indicates the warm side of a bucket and the blue indicates the cold side of a bucket. Instantly the warm water rises to the top and the blue goes to the bottom. You can see you have a cycle going clockwise in this case. So clear to see hot water's rising, cold water's sinking. And that whole motion of the fluid, that is the convection that we are talking about. Now, where can we use something like this? Well, this is a typical process that we used in hot water heaters. In the older days, this was one of the more efficient ways of heating up a house. Is you have a furnace with hot water, which will then rise in a convection cycle, just in the pipes themselves. But then you have what's called a radiator, which allows some of that heat to escape into the room. Warm air will then rise, and then cold air will sink, and you've got a mini convection cycle in each room itself. So you have a convection cycle, which through a radiator will induce more convection cycles, equally distributing heat throughout the house. All right, sorry, I'm trying to get this to move to the next slide. But the final type of heat transfer is radiation. By radiation, we are talking about go figure. Let me get this fixed and I'll be right back. All right, we got it. We got back. Here's an example of convection. Nowadays in our homes, we usually use hot air systems, forced air. It's a little more efficient. However, our body also still runs on convection. The body temperature is regulated by blood flow. As it runs close to the surface of the skin, it transfers heat, allows the excess heat from inside the body to radiate outwards off of the skin. All right, now we're ready to talk about radiation. Radiation is the transfer of energy through electromagnetic waves, or waves of electric and magnetic fields. The most familiar example that we have of radiation is actually visible light. Our own sun has a peak wavelength of radiation of visible light. It gives off more visible light than any other type of electromagnetic wave. Now, how quickly is energy radiated away? Well, the rate of heat is epsilon times sigma times area times temperature to the fourth. Temperature, pretty self-explanatory, temperature of the object emitting radiation. A is the surface area of the object emitting radiation. The sigma is a constant number known as the Stefan-Boltzmann constant, and given here on this slide. And this epsilon is known as the emissivity. How good is an object at emitting radiation? Now, it is important to note here that any object that has any temperature above 0 Kelvin, which means you and me and any object at all that's sitting around you right now, has a temperature greater than 0, so it is going to emit radiation. Yes, you just sitting here watching this video are emitting radiation. So with the emissivity, black objects are really good at absorbing and emitting, so they have an emissivity near 1. Shiny objects are reflecting most of that, so they have an emissivity near 0. Now, if you're sitting in a place where you're radiating more heat than you are absorbing, then it comes to a point where your metabolism can't handle it and you end up getting cold. So we can use infrared sensors to determine the type of radiation that you are giving off as a medical imaging system. Pretty cool. And that concludes